Yo people, what's good? We are going to be going over a moments question. This is for static stuff. Let's get straight into it. There's two parts to this question. There's an A and a B, and we'll go through them both. So, question A. What is the moment at point 4? We're going to try and find the moment at this point here. This is a beam. We can see that it pivots around point A. And we've got 4 different forces that are acting on the beam, represented by the numbers in blue. So, first thing we want to do, we know this has got to do with moments. Let's write out the moment equation. So we know that a moment is equal to a force times by a distance. To be specific, it's normally the perpendicular distance. But in this case, because our force isn't straight away perpendicular to our what's called line of action, we are going to want to try and find the horizontal and vertical components of our force, supposed to trying to find the perpendicular distance. Now you could find the perpendicular distance. Instead, it would be if we took this line down here and this distance here, that would be the perpendicular distance. We'd call it B, for example. But that way, there's quite a few more steps that you have to take and a little bit more room for error, I'd argue. So we're going to do it this way instead. So we've written out the equation. Moment is equal to force times distance. Step 2 is we're going to want to break down the horizontal and vertical components of our force at point 4. So let's draw it out. We've got here, I've actually already forgotten the force, 2 newtons. And the angle is 70 degrees. 70 degrees. So, we've got 2 newtons. We've got our horizontal force, F of x, and our vertical force, F of y. And then we've got the 70 degrees in here. And then we can simply find these by using basic trigonometry. So we say F of x, let me do it in a different color. F of x, so our horizontal force, is going to be equal to 2 times by, and then because it's the adjacent side, it's going to be cos. So 2 cos 70. And our vertical force, F of y, is going to be 2 times by, because it's the opposite side, it's going to be sine of 70. And that force is going to be going upwards, and the x force is going to be going towards the right. So our x force, we can say 2 cos of 70 is roughly 0.684 newtons. And our y force, 2 sine 70, is roughly 1.88 newtons. Right, so we've resolved the forces for the force at point 4. The next step is going to be finding the moment of it. So basically, we're now going to plug this force into our moment equation. So we know that the distance, as we can see here, from our pivot point at point A to the force, we can see it's a distance of 10 meters. And then we want to find the perpendicular force. So the perpendicular force in this case is going to be the y force. As you can see here, it's acting perpendicular to our pivot. The x force, the x component, of the force at point 4 is not included due to the fact that its line of action. So the line of action passes through the x force. So the x force would be going in the other direction. The x force will be going in this direction, and as it passes through the line of action of our beam, it's not considered as part of the moment for this particular equation. So, plugging in our y force, we can then say moment is equal to force times distance. Let's just clarify. So the moment, and we're going to assume that positive moments are going in the anti-clockwise direction. So anything moving this way is going to be a positive moment. Anything moving this way is going to be a negative moment. So it's equal to our y force, because this is just a 0.4, times by the distance, which is 10 meters, which is therefore equal to 18.8 Newton meters. And then we'll just specify, in case you've got a different signing convention, that it's going anti-clockwise. Sweet, that's part A done. Now on to part B. So, part B says we've got an additional force that we need to find. So we've got this force here, F. And it's at, see here, we've got an extra meter added on. Just bear those in mind, okay? So we are asked, what is the value of F needed in order to prevent rotation of beam A? Now you can see I've already highlighted prevent rotation because that should say alarm bell straight away. It should be like, right, this must have something major to do with the question. Prevent rotation, what does this mean? It means we don't want anything moving essentially. So we want it to be in equilibrium. And now the two conditions for equilibrium, like in a situation like this, are the net horizontal and vertical forces. Vertical forces should be equal to 0 newtons. So that means the vertical forces should total out to being equal to 0, and the horizontal forces should total out to being equal to 0. And number 2 is that the moments about any point should also be equal to 0. Now in this particular case, we're going to be taking moments about point A here, our pivot point. And the first thing that we need to do, so obviously we found the forces of this force here. And we knew from the previous question that the only part of this force that we really care about when trying to find the moment, in this case, is the perpendicular force, which was the vertical force. So we've got one here, we can see, actually let me redraw this one just on the point. So we've got these forces that we care about. So we'll call this Fy2, we'll call this Fy3, and we'll call this Fy4. Now we already found Fy4. This is because, sorry, real quick by the way, the X forces, as said before, they don't matter. This is what they would look like. But because, once again, because they're on the line of action, because the forces are on the line of action of our beam, they are not considered for the moment. Essentially because they're not perpendicular. So, to solve this, the next step we're going to have to take is we're going to have to resolve the vertical forces for the forces that we don't know. So we're going to have to resolve the vertical forces for number 2 and number 3. For 2 and 3. So let's start with number 2. We can see here we've got 4 newtons. And this angle here is 55 degrees. And we want to find the force, this force here. This Fy force, Fy2. So, once again, it's pretty simple just trigonometry. Fy2 is equal to, let me just draw this out so it's a bit easier to see, 455 degrees. What else do we know? That's it. This is what we want to find, Fy2. So we can therefore say Fy2 would be equal to 4, and because it's the adjacent side, it's going to be 4 cos 55, which is equal to 2.29. Sweet, that's that one done. Then we got to do number 3. So the vertical force at number 3 is what we're trying to find next. Number 3. We have got, what is it? It is 60 degrees. This angle here is 60 degrees. And it's 5 newtons. Now we want to find this Fy3. I'll draw it here as well. It's the same thing, but Fy3. So we are going to say Fy3. Literally pretty similar steps. This here is going to be 30 degrees. So we can say Fy3 is going to be equal to 5. What's that? Cos 30. Which is equal to roughly 4.33 newtons. And then we'll just clarify for our number 4 in part 1, which we figured out. We said that, where was it? F of y. So F of y4 is equal to 1.88 newtons. Right, sweet. So now we've got all of our vertical forces, all of the forces essentially that we care about to find the moments about point A and to find what value we need for F. So the next step now is going to be, we want to take the moments that we know. So this, we are going to assume really quick, same as in part A, that a positive moment is going in the anti-clockwise direction and a negative moment is going in the clockwise direction. So if we take moments about point A, I'm just going to write it here, about point A, moments in the positive direction, we have got 8 newtons at a distance of 2 meters. As we can see here, 2 meters, 8 newtons. Then we've got this one, Fy2. So Fy2 is going in the positive direction as well, at a distance of 6 meters. Fy2 times by 6 meters, plus Fy3 is also in the positive direction, at a distance of 9 meters. Fy3 times by 9 plus Fy4 is at a distance of, how many is that? 10 meters. And Fy4 we said was 1.88. Fy4 times by 10 meters plus, notice how these have all been going upwards. So they all have been positive moments because of our sign convention. So because we stated positive moments going this way, they have all been plus. So we haven't yet seen a minus. But with F here, with this blue F, you can see it's going down, which means it's going to be going this way essentially. The moment is going to be going this way. So the force is going down because it's down being the right side of the pivot, if that makes sense. So this is actually going to be a minus. So we're going to change that from plus. This is actually going to be minus F times by, and the distance from the hinge to point F is what? 11 meters. So it's going to be minus 11F. Now, we can simply, let me just move this to the side, equals 0. Now it equals 0 because we said we want to get it to the point where is it? To prevent rotation. So we want it to get it to the point of equilibrium where the moments equal 0. Yup. So we can now say that's what 16 plus Fy2 we said was 2.29. 2.29 times 6 is 13.74 plus Fy3 we said was 4.33 which times by 9 is 38.97 plus Fy4 we said was 1.88 times by 10, 18.8 minus 11F equals 0. Simplifying this, so we can say 16 plus 13.74 plus 38.97 plus 18.8. So we get 87.51 equals 11F. And therefore we can say the force is equal to 87.51 divided by 11, 7.96 newtons. Now this force, we've got to remember, as we've said, that we're assuming that this force is going down. We have to make sure that we remember this force is going down. So we'll just write going down. And that is the answer. So hope you guys enjoyed. If you've got any questions, please leave them in the comment section. This is my first video, so yeah. And yeah, see you guys soon.